everything works. Perfect. So thanks for still being here before the lunch break. So let me first introduce myself. As already said by the chair, my name is Joris van der Vondel. I'm working at the Catholic University of Leuven. And today I will present our work related to molybdenum, germanium nanobridges as building blocks for new superconducting device concepts. So this is based on this work, which is referred here at the bottom. But okay, keeping track of the time. So actually, I should also thank the organizers. I think that's also important for having me, giving the opportunity to have a talk. So thanks for that, and organizing this very beautiful conference. Let's start with the more important things. And then I think I also have to thank a lot of contributors. So we have the team in Leuven. Actually, the main protagonist here was Lucas Nulles, a PhD student, and Helene Darcy. But there is also a very strong collaboration on IMEC, which is actually a research institute next to our university, which are really pushing forward quantum technology. Then we had a visit of Davi, who actually also participated in the memory devices, and a very long ongoing collaboration with the group of Professor Siranek, because I think these nanowires can be tuned very efficiently using electromigration. And finally, the simulations I will show here today, the time-dependent Ginzburg-Landau simulations, are done in the group of Antwerp by Professor Milosevic's group. Okay, so I think compared to the previous talks, it's very simple, the basic building blocks of my talk, and they are summarized here. So we have a simple constriction between superconducting banks, which is a nanobridge. I think the simplicity is also a bit of the power and beauty, because you have, let's say, if you see to the current phase relationship, you have, to some extent, at low angles, a linear current phase relationship, which bends off at higher currents. But the nice thing is that it's tunable, and it's tunable in the sense by very simple and conventional nanofabrication through tuning the width or the length of this nanobridge. So you have a very nice control in nanofabrication, from nanofabrication perspectives. Then a final ingredient actually is we put them in a loop structure. So we have flux quantization, and this gives us actually possibility to tune the vorticity winding of the phase in these devices, which actually gives also access to really read out the exact current phase relationship of these devices. So that's the two basic ingredients. So let me summarize, and I think why nanobridges. The first and simple ideas one can make, as also discussed in the talk of Jonathan Anahori before, is it's a very easy way to make junctions. Of course, it's on a tip, so it's much more complex, but the basic idea is you can simply fabricate nanobridges, and as well you can tune these nanobridges. For example, through electromigration, we put here an aluminium squid, we can send current through the squid, electromigrate, and we can actually change the current phase relationship. Or, as also discussed today, you could also gate it with an electric field, so it gives a lot of potential and flexibility, and combined with simplicity. What we want to move for, but I will not show today, but I think we have first preliminary results, is one can also make a flux qubit, predicted by MoGe, and actually developed, or experimentally verified by the group of Astafiev. You can make a flux qubit by just simply embedding a nanowire into a superconducting loop. So, and again, there is this nice flexibility. You don't need an oxide layer, so it should have potential applications, potential applications in qubit technology. And finally, I think there is also some recent development. One example is here. Since we now have, let's say, these low temperatures, we can also think not just only for qubits, but for other simpler memory type of devices. One can use these loops as well, and I hope to show you at the end of my talk. Okay, so the outlook or the ambition today is I want to show we can control the kinetic conductance. So it's by simple nanofabrication. Then we can understand the absorbed vorticity state. So this is a very standard experiment. Many people do that. You just do IV sweeps and you measure the critical current. And then you see, actually, depending on the vorticity, you see different critical currents, which are used, for example, as sensing purposes. But we wanted to really basically understand how the observation comes to life. And I think we finally, or let's say we get this. And then the final slides of my talk is about once we understood all these concepts at play, try to develop novel devices. Good. So as shown here, so this is the fabricated, so this is the workhorse, so this is the device. It's very simple. There is one E-beam run. We do molybdenum germanium with a PLD system. It's a 25 nanometer molybdenum germanium, and then we cover it with a very thin aluminium layer. This is to protect it actually from oxidation, or let's say crap on the surface. So here is a set of devices. So we start by just changing the lower bottom of these squids, going from also a die-end bridge as on the top, just so a bow tie type of constriction, and we move to longer constrictions. Actually, these were the first device fabrications. Now the resolution and quality is even better by tuning the process. But that's the basic idea. So we can really play around and see what the superconducting properties of these devices are. And indeed, if we can control the kinetic inductance of these nanobridges. So if you summarize these ingredients, you can neglect the geometrical inductance. You can do a small calculation. You get these two simple equations, which are combined, let's say, and they give you, let's say, for the zeroth vorticity state, which is marked in blue, this dependence of the critical current on the magnetic field. One can do that very simply, but the idea is that this slope will give you the insights on the current phase relationship of the nanobridge, while this slope tells you about the bow type structure. The nice thing here is, compared to standard aluminium squids, you have very nice straight lines which are directly related to the fact that you have a linear current phase relationship. So this should be directly an evidence that indeed you have a linear current phase relationship. Keeping in mind, let's say, the coherence length in the molybdenum germanium, which we measured through a field dependence, you have a coherence length of 10 nanometer, which is much smaller than the device geometry. You actually expect this linear current phase relationship. So that's the idea, and then we plotted the dashed lines here. This is for the -1 vorticity state, the 1 vorticity state. So the only thing is it's just shifted, and that's all. Of course, this shift, and this also shows, and I think we show it as well in, we show in our results, why we select molybdenum germanium. It is a high, let's say, resistive material, so it's interesting for quantum phase slips. So this is also ongoing efforts we try. And also it has a very high, so the lambda is very big, which makes that actually you don't see any field modulation along the axis. So you just have a shift of this dependence of the critical current as a function of field with vorticity. And this goes on actually very far. Okay, and that's it. So these are the ingredients. So then, of course, one has to measure them. It's in a 300 millikelvin setup. I just show here, not to show the setup. I think it's just a conventional helix system. But I think what is important is we go from minus currents to positive currents, or vice versa. This is important in the experiment. We have heating present in these systems. And this is something which is always present and we have to take into account, which is obvious to some extent, but we have to take into account if we want to understand the devices. Also, there is, of course, stochasticity related to the phase slip events which are present, and therefore, as shown here, one has to do 10,000 of experiments to get the critical current distribution. So we don't do just one IV measurement, we do a lot, just to get the statistics right. But at the end, I don't discuss today, but this is just how the critical current is determined. Okay, so this is the experiment, 300 millikelvin, and indeed we see if we put these vorticity diamonds onto it, we indeed see a very nice linear phase relationship. It is shifted for different vorticities. Of course, we lack a lot of points on this diamond, but that is related to the experimental principle, which I will try to explain you later. But indeed, we can nicely fit it. We have a linear phase relationship, and so we can even get the numbers. So we can determine the kinetic inductance. And for example, in this case, for the nanobridge, it was 261 picohenry, sorry. So this is a very direct measurement of the linear current phase relationship. So let's try to use this technique as a function of devices. So these were the devices I showed in the beginning. We changed from a symmetric nanobridge, so a bow tie at the bottom, and we start elongating the bottom one. And what we nicely see is by changing the length, we change the kinetic inductance. This is into the formula. And this is nicely seen. So we have a control. So this is dependent by the ratio of L, the length divided by the width. We can nicely control the kinetic inductance. Of course, how nice you can control the kinetic inductance as a function of these parameters definitely depends as well on sample quality. But this gives us really a degree of freedom to change, let's say, the kinetic inductance. So I think we can control, we can measure the kinetic inductance. And we, of course, see a nice dependence which is controlled. And moreover, actually, we also repeat it for several devices. This is really reproducible. If you do it for 5 devices, the numbers are very close. So here, we did on exactly the same sample just to get a bit of insights on the dynamics. I'm not sure if it's very well seen, but the device which we asked to the group of Antwerp for exactly the same dimensions, try to model this using time-dependent Ginzburg lambda. So they started as shown here at the vorticity state of 1. You cross here the vorticity diamond. You indeed generate a phase leap, and this of course depends, or this depends on which branch you're leaving. Then you have a change of the vorticity state going to -2. In the time-dependent Ginzburg lambda, they can easily define, or let's say determine, the vorticity state. And then you go to the 0 vorticity state, so there is a jump to the 0 vorticity state. You can increase your current, and then here happens, let's say, a transition to the normal state. And this is important. I mean, let's say we can nicely model the device using really the correct input parameters. But I think the main takeaway, because the simulations are very dependent on small things, so you can always, I think, get the, let's say, insights. But what is important is that in the time-dependent Ginzburg lambda, you can clearly define exactly which phase jump is happening. So which vorticity jump is happening, which is, of course, what we call in the experiment, it's a hidden phase leap line, because it causes a very abrupt jump in the voltage, which is indetectable in the experiment, or you really have to go to very high time resolution experiments. So, and that's why we call them hidden. They are there, but we cannot observe them, and this, again, is important. So they did it as well as a function of field, so they nicely correspond, let's say, the linear current phase relationship, a bit of rounding at the top of the diamond, but this is because time-dependent Ginzburg lambda also takes into account the depletion of the condensate due to current. So this is not taken into account in our simple model. But so what is very important is that one can include, but in these simulations we did not include heating, which is an important ingredient. And the state preparation is just introduced in the model by just adding fluctuations, doing a zero field cooling, and then you end up with a certain vorticity state to start. You then deterministically scan the IV and see the observed vorticity state changes. So, and that is different, of course, but I think it already grabs the experiments. So this is, let's now come back. So why we see these kind of currents, critical currents, as we measure as a function of field. So to come back to that, let's say, just remind, we started here, so we do an IV sweep, we start at negative current values, and we sweep the current up. That is how the experiment goes. So the first observation, of course, is you only see the tip of the iceberg, which is a pity, because it would be nice for a better resolution to also measure the vorticity, let's say, vorticity diamond here at lower fields. But as stated before, if we want to observe this transition, we should have a highly time-resolved experiment. It's possible, it's not, but I think it's a challenge. So I think there are easier ways to try so. So why do we observe the specific vorticity states? And I think one ingredient which you have to take into account is, of course, the energy of the vorticity states. And obviously, this energy of the vorticity states depends on the magnetic field, as shown here. So the zero vorticity states has the lowest energy at 0, and then it goes, like, depending on the applied field, related to the flux quantum. So this is really important, because it means at 0 field, the 0 vorticity state is definitely the lowest. So, while if you take into account here, in our case, for example, at 3.4 millitesla, the first vorticity state becomes the lowest. So, and this is important because this will rule, let's say, the freezing process. You will always freeze in, or at least to a very high percentage, into the lowest energy state. Let's now go back to one measurement, just to understand one measurement, and then if you understood how one measurement comes alive, you actually also understand the dependence on fields. So let's take here this value at 2 millitesla. What we see is we do an IV sweep from negative currents to positive currents, and we observe the zero state, so the critical current related to the zero vorticity state, and sometimes the one vorticity state. So, and the question is, okay, why? And so we have to take into account, and this is important, if we do these experiments, we have heating. So actually the freezing of the state, so the state initialization happens here. Roughly at, this is the retrapping current, roughly at, let's say 10 microamps. So here. The question is, what state do we initialize? Most probably the lowest energy state, but this is something we have no idea. We only have the end product of the initialization state, and then we increase the current, and the question is, perhaps we are in the zero state, we cross zero, go to 1, and then finally measure 1. The problem is we have no idea. There are too many variables. So this is just to show you, at least directly show, so we plot energy and the probability of finding a state, which directly shows that actually the lowest energy states are definitely the most favorable states, the one you measure the most, which to some extent is already makes sense. But okay, so let's now try to tackle what the final product determines. And to do that, we want to make the experiment more simple. So we want to really know, and I think that's the crucial ingredient, because we have no control on the cooling process, we want to really know where we start at zero current. So how we do that is given as well by the group of BELGIUM, is a state preparation process which actually uses the fact that at certain field values only one state can survive. This is a bit more tricky than this, but that's the idea. So for example, here at these fields, only zero, let's say, has a critical current. If you're, for example, in the vorticity state 1, you would be here, you would simply go to the normal state. That's the idea. So it's like you park your car, and this is the principle. You park your car, but you need a system, let's say, which checks is the car parked on the right spot or not. If it's not on the right spot, you just have to get outside the parking lot, and then you have to try again. So this is the idea. So experimentally, it is very simple. We increase the current exactly at this field value. We increase the current until we are at this region. There we stop, and then only if we are, and this is the selection criteria, the one who checks if your car is parked properly. Here you will check, is it the zero state or not? If it's not the zero state, you will simply go to the normal state, you do again a field cooling, and you start all over again. So you try a second attempt, and this is how you do it. If you do this enough times, you will end up with 100% certainty in the zero vorticity state. As stated, you can do this for all states. You can do this for the one state, but just at different field values. So just select, because of course, as you see, for the one state, you have this region, but you just have to change the field. And so now you have control on the starting process. And this is now the experiment when we start really always at the zero vorticity state. And you nicely see there is a region, if you, in field here, if you start with the zero vorticity state, you end up reading out the zero vorticity state, which of course makes sense. But obviously, there is also a region where you start with the zero vorticity state, but you measure the one vorticity state. And now you finally know that you observed the hidden phase leap, meaning that when you cross the zero vorticity state diamond, it has to jump to 1. And then, of course, afterwards, in your experiment, you will measure the one vorticity state. So you really now have control across the full process, because you know where you start, you know where you end, so you know which transition has to be appeared. So we can compare that, and there is a clear difference. Just keeping track of time. So there is a clear difference. So this is the conventional, what everyone does. No? You start with a negative current, you go to a positive current, and this if you do a state preparation. State preparation, in this case, the zero vorticity state. So of course, again, you measure zero vorticity state here at low fields, because it's the lowest energy, and you start with that. But you nicely see actually that when you go high enough in field, you have these jumps, and it means like if you're high enough in field, you go here, you have a jump, a hidden phase slip, and then you actually detect, for example, in this case, the second vorticity state. Nice thing is what we don't observe, and this is already, I think, an insight, is you never observe, or almost none, a 1. So one single phase slip is not occurring in these experiments. And so this is, I think, something which is also seen in other devices. Moreover, there is an asymmetry from left to right, and this is related because the phase dynamics, depending if you're at the left or the right side of your vorticity diamond happens in the nanobridge or in the constriction. Obviously, these are two different entities, so one expects also different jumps happening at the left and the right side of the vorticity state. So we said the tip of the iceberg, we cannot measure this one, but we can use this jumping of vorticity states when you cross the border. And so what we do now is we start in 0. When we run here, and with the student we tried, you can do this for 24 hours, you remain in the 0 vorticity state. So it is extremely stable. So if you then read out, so we prepare in the 0 vorticity state, we go here, so we remain in the 0 vorticity state, we read out, and we read out the 0 vorticity state. But from the moment we cross this barrier, we do a jump, we come back, and this is not a reversible process. And so what happens is that at some cases, for example here, you will jump, in this case, you will jump to the second state, you measure, and you will have a probability of not measuring the 0 vorticity state. And this is then the process which is explained, but I think it's too technical and goes in deep, but that's the idea. The jump is irreversible. And so the idea is if you mark the onset where you're not where you're not 100% jumping to the 0 vorticity state is marked by these lines, and you can really see now the vorticity diamond in the complete field range. So you see these hidden phase slips in a clever way, not because we can measure them, but at least we can pinpoint because of the final outcome of the experiment. So okay, then actually we tried to build a memory in the same spirit of the group of Bezriadin. What you need is, so they have niobium squid, so it's niobium, and then there are here very small weak links. We thought we can, due to the nature of our fabrication process, do it more controlled. We have a long nanobridge. Why? Because then we have a very big critical phase angle, which actually means that the diamonds are very flat. So it actually means, as shown here, so we can do, again, the critical current measurement. So we have very flat diamonds if we elongate the bridge. So it means that the vorticity state survives at very high fields, and you can acquire a lot of phase changes. So we have a lot of states. So in this case, we do the calculation, we do the fitting. At 0 field, we have 17 states available. So you have like a multi-level memory element. So it was nice to store information, but I think also nice, I didn't discuss here, is also the energy of the states as shown before, and it's of course natural at 0 field, is different. So you can prepare a state, for example, state 2, which is the highest, is very high in energy, and you can use it as a sensor. A single photon detected by your squid will lower the energy of the state, and you can do a readout afterwards. It's a bit similar as a single photon detector. But okay, can we do that? So that's the question now. And we use the principle of before. We have a state preparation protocol with field. We can write all the states, and this is what we believe. No, we can prepare in every vorticity state of these 17 states, and then we go to 0 and we read out. And so this is the result. So indeed, you can clearly define which state you are, going from the 2, 1, 0. So we have actually, in this case, 8 states, which are, so we have a memory where we can store information in 8 states. Be aware, for the preparation, we need magnetic field, but I think this was also like in the work of Giassotto, which I showed in the beginning. But so this is the critical bottleneck, I think, is that it would be nice, of course, to do this at 0 field, so we don't have any field needed or no coils, additional coils to get the memory running, and this is on our to-do list. But so it really shows why we don't see all these lower states. Yeah, this is very simple, because for these states, you will have a hidden phase slip. So you will, so for example, if you prepared in state number 8, you are at very low current, so very low heat. You will have a hidden phase slip going to one of these states here, and you will not be able to distinguish between that state. So only the state, so heating in these devices, to some aspect, it's like with the single photon detectors, is a bonus. It's needed to be able to read out these states. So okay, I think to summarize and to stop before 1, is we can measure and control the kinetic inductance. We can actually identify, because we have this protocol, we can read the initial states, we can define, the initial state, read out the final state. We can really explore phase dynamics without the need of fast experiments. And we gain these insights to create a superconducting memory. So this last is a work in progress. So what to do now, as stated before, is we are now building, or no, this is done, is so high frequency experiments, and to add our resonators and combine them with these type of squids. And the nice thing is, because compared to one of the speakers also today, is, I mean, control of the qubit energy would be really nice. So here we have the ambition to bias actually the SQUID and try to change, let's say, the resonance frequency from that perspective. That's it. I have to thank you for your attention, and I'm open for questions.
Thank you very much, and we have time for questions, comments.
Thank you. I have the following problem. Please help me to relate the notion of a hidden phase slip to a common notion which has been used in this field already a long time, a phase slip. A phase slip has two features. It's an event where in some part of a superconductor there is no uniquely defined phase. And second, it's a topological defect. It's always linked to suppression of the order parameter, maybe locally. Are these two constituents of a common definition of a phase slip present in the hidden phase slip, or we should simply take this new definition as such? Thank you.
No, so it is a phase slip as you define it. It's hidden for the experimentalist in the sense that we cannot measure it, so we cannot detect it. Of course, as stated, we could, because what are the properties? It's a very sharp jump in the voltage. If so, it is hidden, yeah, for me, in the perspective of doing DC measurements. So it's hidden if you just do standard characterization of a SQUID, but it's not hidden if you would do time-resolved measurements with enough speed. It should be present. So from that perspective, it's hidden, but it's a phase slip event.
Yeah, question. So there was usage of time-dependent Ginzburg-Landau equations to simulate motion of phase slips, right?
Yeah.
So is there any attempt to use more fundamental approach as by usage of Ginzburg-Bogoliubov-Dijon theory?
No. This is at this moment there is no, let's say, but I think it's also very difficult due to the size of the device. But at this moment there is not, because at the end the physics is grabbed by this very simple model, and we don't have the ambition to really, I think also the physics is settled of this weakling, so I think we don't get more insights. I think it becomes important, this type of more extended, if you are really interested in the microscopic physics of the weakling, which in our case is just a wire. It's a very simple case.
Well, just the dynamics of quasi-particles can tell us a lot about how the system approaches equilibrium, and also can give us the insight into possible, eigenenergies and things like that. I mean.
Yeah, no, but I think anyway, perhaps it was a negative response. I think if someone can do that for us, it would be great. And if we can learn from these simulations, I think definitely we have, certainly as well with the spectroscopy kicking in, I think we can do much more related to really the states and the dynamics in these devices. So I think it is worth to, at this moment, we haven't done it because we don't do it, so we need a partner. That's the idea.
Thank you.
Yeah.
So I have a question. So these transition vorticity, they are two phases. They are first-order transitions. I wonder if you can get like a latent hit of those transitions, or I mean, is there a way like from the irreversibility? I guess you see what I mean? I mean, probably you can go like sort of superheating state, and then and supercooling, and perhaps from that size you can get. But I don't know if you see that, or I'm completely missing the target here.
No, I think the process itself now at the moment is not studied. We just see the end product. But I think, for example, if one be able to measure, let's say, locally temperature, I think that would be an interesting while going through this transition. This I agree, but now we just see, we know there is a phase slip. We actually know where it, let's say, where it happens, but with the phase slip event itself, we don't explore at all.
Yeah.
But I think indeed it's an interesting question to see this transition and how it behaves. But then perhaps we need
Yeah, we'll discuss.
a temperature sensor with a very high resolution, which I think was presented before me. Okay.